Hello, welcome back to Engineering 211 Statics, and I'd like to start today by talking about moments. One thing, if you're following along in the textbook, we've skipped Chapter 3. Chapter 3 is very important material. We're going to come back to it, but your author chooses to talk about equilibrium of a point before talking about a moment, and I choose to talk about a moment and then talk about equilibrium of a point and equilibrium of a rigid body, which is doing Chapter 3 and Chapter 5 essentially simultaneously. So we're gonna. It's all good material. It's a lot of people do it both one way or another. It's very common to do it one way or another. So we're going to tackle from Chapter 2 to Chapter 4, and then come back and do Chapters 3 and 5 together. So be aware of that as you go through your reading of the textbook. Well, the concept of a moment is, if we were to define it, it's the rotational tendency. Let me write this out here and talk then a little bit about it. Okay, so we could say that the moment is the rotational tendency that a force may have on a body to rotate about a point or a line. We could replace line with axes. The rotational tendency that a force may have on a body to rotate about a point or line. And probably the most important word here, key word, is tendency. A lot of times students will say, well, it's not rotating, so there's no moment. Well, no, that's not true. It only has to have a tendency to rotate. We talk about this moment because let's say that we look at a point and you have a couple of forces applied to this point, and so we'll have 10 pounds acting down and 10 pounds acting up, and if we look at the sum of the forces in the vertical direction, we would know that we would have 10 up minus 10 down, so that would be equal to 0. In fact, we'll be doing a lot of that when we get into equilibrium. That's Chapters 3 and Chapters 5. But if we change things up a little bit, maybe it's instead of a point, it's a body, and we apply our force here of 10 pounds and our force here of 10 pounds, and again you sum the forces in the vertical direction, setting that equal to 0. We got 10 up, looking at this, summing up the forces in the vertical direction. I got a little hasty with the 0 there. Looking at the forces in the vertical direction, we've got 10 up, and we'd subtract the 10 down, and this again would be equal to 0. Now, people are uneasy with this one because they say there's more going on, and indeed there is. It's going to have a tendency to rotate. Anyone that has maybe tightened the cap on a bottle recognizes this. This would be a model of putting your thumb here and your finger there as you try and twist the cap or lid onto something. And even if that gets tight, there's still a tendency to rotate. Well, we can quantify the moment. We can say that the moment is equal to, and maybe I should introduce it in vector form first, that the moment is equal to r crossed with f. And when we start looking at three-dimensional problems, we're going to use this equation a lot. This is the cross product. So we'll have to do some development work on that. The reason I introduce it this way is we want to recognize that this is a vector. The cross product returns a vector, so the moment is a vector, which means it has a magnitude and a direction. Okay, there's the size of the tendency, and there's also the direction of the tendency. Is it going to rotate clockwise? Is it going to rotate counterclockwise? And what magnitude is that? For our purposes right now, as we get started in this, we could say that the moment, and if I'm just looking at the magnitude, is equal to force times distance. Okay, because we see the distance crossed with F. This cross product, the order is important here, and we'll talk about that. But for our purpose, we can say that this is the force times the distance from the force to the line of action, distance to the line of action of the force. So we'll say this is distance to line of distance to the line of action of the force. So for instance, we take this problem here as monkey wrench. I'm not sure whether we can say monkey wrench anymore, whether that's not politically correct or not. I'm not sure where that term came from. If you don't like that, you could call it some sort of a spanner, or you could work up your best English or Sean Connery accent and call it a spawner. Anyway, so we've got this wrench here. You draw whatever kind of wrench you want. These used to be way more common than they are now. And we've applied some force to this. Okay? And if I'm looking about for the moment at this point here, maybe I would say that that is O. I can talk about the moment about O as being equal to this force F times a distance here. A distance, we will call this distance D. Okay, and I usually try not to put this symbol in here. I don't want to confuse it with the dot product, but I'll keep that as a dot multiplying. That is force times distance. Okay, force times distance. So that's the force that we have, and this force has a line of action here. We multiply that force times the perpendicular distance to the line of action of the force. Now that's the magnitude, and then we'd have to look at this and say which way is it going to rotate. It's pretty easy, particularly where you have a piece of paper there. If you were to pin this down, quite literally put a tack there, and then apply a force here, this whole thing is going to rotate which way about that? It's going to rotate clockwise about that, isn't it? Okay, so we have our magnitude here, and then our direction would be indicated like that, or we could say that it is clockwise. Clockwise versus counterclockwise, or I guess if you're sticking with the English thing, the English accent, you could call it anti-clockwise. So I think they use that term a little more. A couple other things that we might look at are the units. What kind of units would we have here? Probably force times distance. We would have pound feet, or we would have maybe Newton meters, or maybe pound inches, something like that. Okay. It'll come up, we might talk about foot pounds. Usually your author is going to try and make sure I get this correct for you here. Double check. Yeah, I think we're okay. So usually we use the terminology pound feet when we're talking about this. Technically, the order here, you could reverse this order and have foot pounds, but you'll also notice that this is the same equation that we get for work, force times distance. So usually we use this order here, foot pounds, when we're talking about work, and we use pound feet when we're talking about the moment or the torque. Incidentally, we could use the term torque interchangeably here. We'll use almost exclusively the term moment. If someone talks about torque, that's the same thing. So if we're talking about moment and torque, we'll talk about pound feet. If we're talking about work, we'll talk about foot pounds. Now, in the end, I'll probably be pretty happy if you have the units at all. So it is force times distance, but if you see someone talking and making a big deal about pound-feet versus foot-pounds, that's what's going on. Some other common units would be Newton meters in the metric system, or sometimes if we have a smaller value, it would be pound inches. Maybe you've heard them say that something needs to be tightened up to a certain amount of pound-feet or pound inches, and that's what you have going on there. Well, with that introduction, let's move on to some very easy examples, conceptual examples I might call them, to make sure that we have this concept at hand. So let's try something like this, maybe a simple cantilevered beam. And we'll say that we have this point there, O, and we'll apply a force here, say P. We can say that this distance is L. And if I ask for the moment about O here, what is that equal to? Well, we can say that the moment about O is equal to the force, that's P, and you could think of that force acting, shooting through space like an arrow. There's its line of action, and its perpendicular distance is L. So we would have P times L, and does it have a direction? Yeah, it's going to tend to rotate this thing. If you were to pin this down here, it would tend to rotate that clockwise. So we could indicate that with a clockwise arrow. So that's one example. Let's try another one. I'll get progressively a little more difficult or tricky with these. We'll try something like this. There is a P, and let's say this is a lowercase l. There's uppercase L. We'll say that that is point O. So if I look at the moment about O here, I could say that that is equal to what? Well, I have the force, that's P, times what's its line of action? Its line of action is there. So if I look at the perpendicular distance between O and P, that is given as the distance L, isn't it? So it's P times lowercase l. And it's also going to, if you pin this point, it's going to rotate clockwise. Now some people will be disturbed that this uppercase L didn't factor in there, which is absolutely correct. If you have maybe a sign or something, and you have a post out here, and you have a arm then, and you have it's supporting some sort of a load here, this is your critical dimension as far as the moment goes, a moment about this point here. This distance here, the height of this thing, has no bearing on that. Okay, let's try another one. Let's try something like this. A little bit of trig involved here. Or we can say that this distance here is L. We'll say that this is O. I'm going to apply the force F. We'll mix up the variables a little bit. We'll say that this is 30 degrees in there, and we'll say that this is lowercase l. So we can, if we look for the moment about O in this one, say that it's equal to the force F. There's that force F. That's pretty straightforward there. And then I have to come up with effectively that whole distance there, don't I? So that's going to be lowercase l. That gets me this part there. And then what's this piece here? Well, that's L times the cosine of 30, isn't it? That's why we studied right triangle trig. So we've got plus L cosine of 30. So force times distance, the distance being uppercase L times lowercase l cosine 30. What direction do we have? Again, if they're asking for the moment, we'd like the direction. It's clockwise, I believe. If you pin that there, it's going to tend to rotate clockwise. Well, let's try one more here. So we'll go back, we'll apply a force P here, and maybe I'll say this distance is A, this distance is B, and this distance is C. And again, I will put that as O. So I'd like to find the moment about O. So what's that going to be equal to? Well, there's my force, the line of action of the force. There's the line of action of the force, isn't it? So I need to find this perpendicular distance. So I can say the moment about O is P times the distance. What's that going to be? A minus C. P times A minus C. You'll notice that B has no bearing on that. Okay, B is not a player here. It doesn't matter. And this is one, if we pin it here, that's going to rotate which way? You apply a force that direction, this is going to rotate like that, isn't it? So that would be counterclockwise. Okay, counterclockwise. So those are some, hopefully, good examples. Now, some of you might still be laughing at our how cryptic our spanner wrench was there, or monkey wrench. And I don't use those a lot anymore, because when you used to work on your Model T or Model A, you had lots of room to use wrenches like that. But in more modern mechanical things, things have got closer together. It's hard to get into things. And sometimes you can't apply maybe a force at a nice right angle like that. I'm not doing very well drawing this bolt or not, am I? There we go. Okay, so that's okay, not great. So we'll draw our monkey wrench here. Like this. And I drew the force like this, didn't I? You might say, well, yeah, good luck getting that in there. Sometimes you have to apply the force at an angle. Okay, well, that's fine. You can then look at the line of action here. And if you happen to be looking for the moment about this point, then you need to find this perpendicular distance right there, don't you? Well, sometimes that distance is kind of hard to find. We might know this distance here. So that's D1. And we might know this distance here. We could call that D2. We could, with some geometry, maybe find this, but there's an easier way to do this, and that is Varignon's theorem. So I'd say this problem is a motivation for Varignon's theorem. Sure I got that spelled right. And what Varignon's theorem says is that the moment of a force about any point is equal to the sum of the moments of the components of the force about the same point. The moment Okay, so let's see how I did here. The moment of a force about a point is equal to the sum of the moments of the components of the force about the same point. We could probably add a few words here. The moment of a force about any point, you could say any point, is equal to the sum of the moments of the components of the force about the same point. And you have to be careful here. Maybe I should add the word, I haven't mentioned this so far, but we should probably say algebraic sum. If it tends to rotate it clockwise, we need to handle it different than if it rotates it counterclockwise. So the direction is important in regards to whether it's going clockwise or counterclockwise. So this is kind of nice. We can break a force into its components. So in this particular case here, we could break this force into its component like this and its component like that, and then these distances would be a lot more useful. Well, I'd like to try a very simple example of this and see if we can get that to work out. So let's say someone comes along with a problem like this. And maybe we have, we'll say, 4 meters there. And we've got a force here. I haven't drawn it to a very good scale because I'm going to say that this is 2 meters. And we'll say that that is point O. Okay, and we're applying at this downward angle here. We'll say that this is 40 degrees, and I have 600 newtons, or in the English system. And we'd like to, given this, we'd like to find the moment about O. Okay, we'd like to find the moment about O. Well, there's a couple ways that we can do this. We can do it without Vrignon's theorem. So let me try that without Vrignon's. So that would look like, I'll draw this in a, and this could be really any, you know, if you're a mechanical engineer, it might be some sort of a bracket, although it'd be a big one with 4 meters, about a little over 12 feet, or a structural piece if you're a civil engineer. But if I were to draw this a little bit more schematically, get something that looks like this. So I could say that this is 2 meters here. I'm just drawing basically the outline there. This is my point O. There's 4 meters. And what I'm going to do is I'm going to put this force here. We said that this was 600 newtons, and we have this down angle of 40 degrees. Now what I'm going to do is I'm going to drop a perpendicular to this force. So that's a perpendicular. And let's see, I like putting perpendiculars in, so I'll put a perpendicular like that, and maybe I'll put one more perpendicular there. So if that's a right angle, that's a right angle, that's a right angle, this has to be a right angle, so this becomes what, 50. If that's a right angle, this is 40, and then this whole thing's a right angle, so that is 50, which leaves me with this at 40. And I think that's correct. So now if I would like this side here, I could talk about this as what? 4 times the cosine of 40. And we could use the sine of 50. I'm going to stick with the cosine of 40 because I don't write things in terms of 40, and you'll see that in the end, why that might be advantageous. And if I look at this side here, which would be the same as that side there, I could say that that was 2 times the sine of 40. This side here, 2 sine of 40. So I could then say that the moment about O is equal to 600 newtons times the distance, 4 cosine of 40 plus 2 sine of 40. And when you run through the math on that, that turns out to be, get that right, 600, 4 cosine 40, 2 sine, yeah, that turns out to be equal to 2610 Newton meters. Force times distance, Newton meters. That would be my answer. No, not quite my answer. I still got to do, they're both going, it's going to cause it to rotate clockwise, isn't it? Well, let's try it then with. Now come back and compare this. Let's try it with Varignons. And with Varignons, again, I will draw this a little bit more schematically. There's O. I have 2 meters and 4 meters. And I'm applying this force here like this. 600 newtons. 40 degrees. And what Varignon said, well, hey, you can just break that into its components. So I can break this into this component, and I can break that into that component, and this would be 600 times the cosine of 40. This would be 600 times the sine of 40. And with that, I could effectively remove that, right? Because we know if I add these two vectors tip to tail, if I take this one, which is 600 cosine 40, and add it to this one, tip to tail, 600 sine 40, my resultant is that 600. Okay, we spent chapter 2 talking about that. So now what I can do is I can use those components and talk about the moment about O being equal to this 600 times the cosine of 40. That's that force there that acts along this line, so it's acting through a distance of 4 meters. And we have to add to that 600 times the sine of 40. That's that force there that's acting along this line, and that's acting through what? 2 meters. Now we've seen this math before. We have 600 times 4 times cosine of 40, there's that, and 600 times the sine of 40 times 2, that's that. Okay. Basically, Varignon's theorem says that you can do distribution. You can do distributive math. That's what you have there. You should get exactly the same answer with this. 2610 Newton meters. It's going to rotate clockwise. Both of these rotated clockwise, and that's why we got to add these together, and that's the sticky part. Our next example I'll try and do is one of them would go in the other direction. We have to be very careful to treat it properly. Okay? So there's nothing wrong with either method. I think sometimes if you're in a high-stress situation, in a timed event like a test, sometimes coming up with all these perpendiculars and these geometry relationships can be trying, whereas Varignon's theorem allows you to do it with a much more mechanical method. Break it into its components and put it back together. So hopefully that's a good and useful demonstration of Varignon's theorem. Well, let's go back to that monkey wrench or spanner wrench. I think I posed the question back on page number 3. What happens if this is at an angle? So let's try that. So a bolt seems to be getting what? More and more oblong. Maybe if you're watching it on a monitor that skews it, maybe it'll be back to where it should be. Okay, and let's say that I have a force applied like this. I'll take this angle in here as, let's say, 20 degrees. We'll say that this is 100 pounds. And we'll say that this, we're looking at the point O, so the distance here we'll say is 1 foot, and the distance here is 3 inches. And we'd like to find the moment about O. Okay, that's our problem. So what's the first thing we should do? Well, probably the first thing we should do is get consistent units. I said dimensional homogeneity would creep up on us like a snake in the grass, and you're going to be careful here. This is 1 foot, that's 3 inches, so we're either going to have to change this to 12 inches and get our answer in pound inches, or we could get this in terms of feet, which is what I think I will do. I'll convert that 3 inches and say that it is really 1/4 of a foot. Okay. And then what I'm going to do is I'm going to break this up. I'm going to say that this force would be what? 100 times the cosine of 20. And this one would be 100 times the sine of 20. Is that right? I'm just looking at a right triangle here. I've got the hypotenuse, that's 100. And this angle in here is 20. This is a right angle. Yep, this is going to be cosine right there. 100 cosine 20. That's this piece. And this piece here would be the 100 sine 20. Okay, so I can say then that the moment about O, and this is where I have to be careful because it looks like, we summon the moment about O, if I look at this, this one tends to rotate it clockwise, doesn't it? Whereas this one is going to be acting along here and tend to rotate it counterclockwise. So why don't I go ahead and say that I take clockwise as positive. I'm just going to do that arbitrarily. Bear with me. I'll try it the other way too and show you we should be able to get the same answer. So if I take clockwise as positive, we've got 100 times the cosine of 20 times the distance that acts through, which is 1. And then that's positive because it's rotating it clockwise. This one is negative because it tends to rotate it counterclockwise. This should probably be acting up here at the middle of that bar. Excuse me. So I've got minus, because this rotates it counterclockwise, minus 100 times the sine of 20 times the distance that acts through. So that's going to act through this distance here, which we said was that 3 inches, or in our proper units, 1/4 of a foot. Okay. When you run through the math on this, what does that turn out to be? Let's see, 2 sine. Okay, my calculator's giving me 2 different answers. I'm going to have to start over on this, but good. That'll give you time to grab your calculator and try it. Let me do this again. I think we can make that work. That's what I was expecting. 85.4, that would be pound-feet. And that's going to be which way? Well, we've taken clockwise as positive. This turns out to be a positive number. So it's like that, right? Now, let's say that we would have taken counterclockwise as positive. Well, this would have looked like this, wouldn't it? The sum of the moment about O would have been a minus 100 times the cosine of 20 times the distance of 1 plus now, because this is rotating it counterclockwise, so that would be a plus 100 sine of 20 times the distance of 1/4. I run through my math here to double check that first answer. This one turns out to be minus 85.4. Well, the negative over here, this one was positive, so we knew it was going in this direction. This one is negative, so I mean we could say it was negative in the counterclockwise direction. That's a little bit like saying we're not gonna have school on Monday. So let's get rid of this negative sign and flip that direction. So we would end up with positive 85.4 instead of minus 85.4 in the counterclockwise direction. We have positive 85.4 in the clockwise direction. Of course, this would have the same units of pound-feet. Okay, so we get the same answer: 85.4 pound-feet clockwise, 85.4 pound-feet clockwise. It's good. And the reason I ran through this on the calculator, I want to make sure the magnitude was the same. Double checking my work. I seem to have trouble getting this first one out of there. But so I think we're good with that. So as long as you're consistent, whether you take clockwise as positive or counterclockwise as positive, you will get to the right answer. I would definitely on this one take this thing, cover this up, see if you go back and tackle that question yourself. Lots of little pieces there, all of them fairly easy, but easy pitfalls. Units, make sure you get consistent units, use Varignon's theorem, right triangle trigonometry, and then put it all together. So one of the things that we're going to do then as we move on, so this would be page 5, is we're going to look at what this looks like in 3 dimensions. So we're going to go back to the moment and explore the equation. The moment's equal to r crossed with f. So we're going to have to talk about the cross product and the implications there, the need for a right-hand coordinate system. So that's going to require us to take a little time out and do some math and whatnot. So that's good. Before we go into that, we'll leave that for next time. Before I go into that, I'd like to talk maybe a little bit about what some values for torque or moment are. So let's talk about lug nuts and the moment or torque. So we'll put this in pound-feet of torque. You're getting a little tired and sloppy there. Pound-foot of torque. So let's say that we have a passenger car. You could probably look it up in your owner's manual. If you ever change the tire, you should look it up. How much pound-foot? Probably going to be somewhere about 75 to about 100 pound-feet of torque. Okay, and again, you'd want to look that up. It's going to depend on how big the car is, how many lug nuts it has, and things like that. If we go to a 3/4 ton pickup, we're probably looking somewhere between about 120 to about 170 pound-feet of torque. If you start to get into large trucks, let's say class 8, we usually have someone that's working their way through school at Les Schwab as these numbers kind of off the top of their head. And again, they're different for different vehicles, but these are the general ranges. You're going to be somewhere probably in the around 400 pound-feet for class 8. That's the classic 18-wheeler, the semi-truck, or maybe a big garbage truck or something like that. Garbage truck, not necessarily class 8, but something about that size. So that gives you some idea. If you've ever changed a tire, you have some idea. They actually have wrenches that are calibrated to give you some indication of this torque. There are some critical fasteners, and probably lug nuts are fairly critical. You want to get them tight enough. You don't want them to come off. A lot of places, once they put the tire on, they'll check and make sure that the lug nut is tight enough. And there's lots of different ways to do this. But to give you some idea, because a lot of times we'll talk about, we come back to this number like this, 85.4 pound-feet. And what does that mean? Does that really mean anything? And when you then look at it in a context like this, hopefully it means a little more. So fire up your homework problems, practice Varignon's theorem, practice this concept, and I will talk to you next time. Thanks for watching the video, and take care till then.